We've talked about a lot of things so far. We've talked about period and frequency and how they're related. We've got formulas for those. We've talked about how the wavelength and the frequency and the velocity of the wave, the speed at which it's traveling, are all related. So we've got the formulas for those. But we still don't know some of the very basic things about waves. First off, there's two kinds of waves. The wave that I'm sending out right now is what we call a traveling wave. So that velocity, right, that wave that's being sent out, it's being sent out like that, right? It's being sent out as a pulse, right? You hear it go away, and it never comes back. You never see it again, right? So that right there, wave that goes away from you and never comes back. Traveling wave, a wave that keeps on going, right? So a traveling wave is one that just keeps on going out the door, right? So if I draw, a progression of this thing, if I have a transverse wave, there's my string or my snake, whatever the case may be, right? And then sometime, so here's your beginning, here's your middle, here's your end, right? So some other time you have your wave along here, right? I guess I didn't have that much of a wave to it, whatever. There you go. And then later on, your pulse of your wave is all the way over at the end, okay? So beginning, middle, and end. That's how your traveling wave goes. And it travels, again, pretty obviously in that direction, okay? So that's one kind of a wave. What's another kind? Well, one that reflects back at you. So check this out. Now if I take this snake and I take and send a wave down, it dampens so you can't really see it, but you can notice after the wave goes by, the bottom of it still appears to be vibrating. And if you look really closely, what you'll see is the wave goes over, right? Really dramatic there. The wave goes over. Good grief. Too many things in my hands. That's what's going on here. All right. So as I go, the wave goes over, right? But if you look really closely, you will then see the wave bounce back. And it's really dampened. Dampened is another term too. It basically means you're killing the vibration, right? So if you hear something ringing like a bell, okay, that's freely vibrating and freely oscillating. You put your hand up against it and all of a sudden it stops making a sound because your hand absorbed the vibration and killed the vibration, okay? So if I send this over, look, the snake still dances and again, the wave comes back towards me. Now it's a lot more obvious with the slinky, hopefully, okay? If I send a wave along it, hopefully I can get this high enough contrast here you can see it, you can all of a sudden see it keeps vibrating the whole time. I only gave it one pulse, but it keeps vibrating, right? So I gave it one pulse of a wavelength, and it just keeps on coming back to me, okay? So the second kind of a wave, traveling, just keeps on going. Never see it again, okay? The second kind is a reflected wave. A reflected wave, if I were to draw that one out as a transverse wave, here's what happens with a reflected wave. At the beginning, you get a pulse, just like you did in the first case. Somewhere in the middle, let's go ahead and say this one is all the way at the end now. Oof, I need to go the other way. It goes this way, okay, there it's at the end. And at the end, what happens? So this wave's going this way, this wave's still going this way, but it's tied or it's anchored somewhere out of that point. And so what happens now is that your wave then comes back up and then down. So now your wave is coming back at you. Sorry, I took a second to reverse it in my brain. It's not going terribly fast there. So now you can get this thing coming back, okay? So where do you see a reflected wave? Well, with sound waves, if you have sound waves going out like this, right? If they hit something and bounce back at you, we call that an echo. So an echo is a reflected wave. And here we go. Sound waves going out, never coming back. Sound waves hitting a barrier and echoing, reflected back at me. I don't know if you guys, hopefully you can pick that up in the sound. I'll get really close and uncomfortable, okay? Sound wave going far, far away and never coming back. Sound wave coming right back towards my face. See how that works? So you get a reflected wave where it's coming back at you. This is where things can get really interesting, okay? So if we send out a ton of waves, not just one, but we put a bunch, we have a regular oscillation to something, right? So instead of shaking a rope one time or a slinky one time or compressing and releasing a slinky one time, we just send pulse after pulse after pulse along it. What happens then? Well, if you get pulse after pulse on a string, let's see if I can even do that on here. Well, look at this. You can get a lot of different waves built up on one, right? They still could be traveling at wave, as a traveling wave going out the door and never coming back, okay? So a traveling wave would just do this, and that would be kind of interesting on its own, right? Going this way. Lots of pulses. This thing's going up, and down to make these, the amplitude to make that oscillation, okay? But it's still going this way and going out the door, okay? So what happens if we tie the end and it gets reflected back at us? Now that's where things get interesting, okay? Because what you can do is you can create something called a standing wave. What is a standing wave? It's a special case, okay? So first off, I guess I'm getting overly excited here. I need to stop, hold up, and come back, okay? If a wave gets reflected back at me, look at what happens if we have multiple pulses in here, okay? When one of these waves comes back, you could potentially have a wave going like this, and a wave that is already coming back along the same. It's going like this. So this one's traveling this way, this one's traveling this way. What happens when they meet in the middle? Well, it depends, okay? It depends. So if what you get is this wave, okay, overlapping this wave, which is what's going to eventually happen, it depends on how they overlap, okay? If you get them to overlap where this wave is like this, you have a really low low here and a low low here, so they add together and you get a wave. When I combine the two together, right, I will get from this, I will get a peak here that's normal, a really low low, and then a regular peak that's normal over here, okay? What happens is it propagates further, okay? So if they don't line up like this, what happens if they line up where you have a low here and a high here? Well, the high and the low there meet up and they cancel out. So in this case, what you actually get, instead of this exacerbation of things, instead of like making it larger, right, or accentuating it, what you get is the low and the high canceling out. That's just a simple addition here is what happens, right? You have a minus here, you have a plus there, so they actually cancel out to be something like 0. So for this point, a low and a high cancel, and over here you have a minus and you have a plus, so you add them together and you end up with a cancellation. So at that point at which these things overlap each other and the trough and the peak overlap, you get nothing. You get a flat line. And when they pass each other afterwards, after this moment, right, then you get here, you got a peak over a peak and a trough. Well, let me draw this out a little better. You get a peak over a peak and a trough out here. Then from this one, what you'll get is a plus here and a plus there. So those pluses will add up. You'll still have your regular trough over here, flat line over there, and then you'll have this peak over a peak, so you'll get a really high peak, right? So it actually exacerbates it, it stretches it out, okay? What this is called is when things overlap like this, and they either add up together or they cancel each other out, it's called interference. And think about it, that term kind of even makes sense. Waves messing with each other, right? They're interfering with each other. So they can either interfere with each other where they help each other and grow, or they can interfere with each other and cancel each other out, okay? And one set of waves can do both as they travel against each other. So you can have both the canceling out type of interference, which, by the way, when they cancel out, that is called destructive interference because they're hurting each other, they're tearing each other down, right? So destructive interference is where things flatline. The other kind, if you tear something down, you call it destruction. What do you call it when you build something up? Construction, right? So if you get a really high peak and a really low low from these things overlapping, that is constructive interference, okay? So a couple kinds of interference, traveling wave versus reflected wave. Now, I got overly excited before, so let's go ahead and talk about standing waves. And it turns out that standing waves have a lot to do with this interference. In fact, they have everything to do with this interference. And it has to do with the frequency of the wave too, right? One wave going along has to be the same frequency as the other wave coming back, and they have to line up in a certain special way. And when they do, you will get something really cool happening. What you will get is you'll get wave going and coming back, right? Only oscillated once, still vibrating because that energy is going back and forth, right? So there it is, there's our wave. And if you look at this, when I vibrate it like that, I can only get it to go up and then back down, right? The whole thing is doing this. It's going up, and then it's coming back down. Hopefully you guys can see that. Maybe it's better here. It goes up and then back down. That's about as many waves as I can get into it easily, right? So if I do that, okay, what happens if I take and I get it dancing along? Well, look at this. Now this is interesting. So you can hopefully maybe slightly see that the thing is actually going, if I hit the right frequency, right? If I hit the right frequency, it is going up to the same peak every time in the middle, coming back down to the same trough every time in the middle. And the ends are staying constant and consistent. So what you see with this special kind of constructive and destructive interference is you have now those things happening along the same string or slinky or what have you. You have the wave going and building up, and so then it goes up, and then when it has constructive interference the other way, it can go this way, and in between, if those waves are exactly, so if they're, redraw this, reset. Okay, so if I have a wave A going this way, and I have wave B going this way, what do I get? I get a flat one, okay? They can destructively interfere with each other. If I have wave A going up and wave B also going up at the same time, what do I get? From this one, I will get constructive interference, a really high wave. What if I get the troughs matching up? Wave A is like this, wave B then travels and overlaps it, and it also does that. What do I get? I get a really low low. But the ends, the end points of that slinky, okay? The end points of that slinky, put that in the middle so it's a little bit easier to see. The end points over here stay in the exact same spot. No matter what you do, they never actually move. So those points right there, the ones that don't move, are called, not N, or M, N, a node. A node is a point on a wave that essentially doesn't move. You really see them mostly, almost entirely, on a standing wave. So let me just show you again. I'm going to get this thing, and all I can do is get 1/2 of a wave, right? I can only get half of a wave on the slinky. So if I get it going, look, it'll go up and down. If you freeze it and zoom in, or pause it and just kind of look at it, you'll see at some points the slinky's flatlined because it's destructively interfere with itself. Other times the troughs will add up and you'll get this, right? You get this kind of like low trough like this. And other times you'll get this kind of mound like this, right? Oh, except for much larger, right? But you'll get that constructive interference of the peaks, okay? But the ends never change because I've got a standing wave, also sometimes called a dancing wave, rarely. But standing wave, it's standing in the same place, it's just oscillating up and down. Basically like it's kind of like standing in place. It's not actually. The waves are traveling there, they're traveling back, but as they go past each other, if they overlap, you get a really tall wave, right? And if they overlap like this, there we go, like this, right? Then you get a flat line. If they overlap like this, you get a really low low, okay? So that's your standing wave for you, okay? And we're gonna talk more about those in a little bit because they get to some really interesting things later on, okay? But nodes, the points that don't move, crest and trough will oscillate back and forth and trade places and flatline even, okay? But the nodes never change. A node is a point that doesn't move on a standing wave, much like this. And if I look at it, I don't know if I can get it to be a little bit easier to see somewhere, anywhere, maybe over here. No, that's not any better. Okay, so if I get it so you can kind of see it, you can see it's got 1/2 of a wavelength going on at any point in time. What if I start vibrating it more? Well, what you're going to start to see, actually I don't need to go any higher, I just need to go faster, right? There we go. Now you're going to see that it's starting to kind of get a node in the middle of this thing that is also not moving, so you can see that I'm not totally full of it, right? If I get the frequency just right, what you're going to see is a full wavelength along the thing, and if I could go faster still, you might be able to see a third node popping up in there. Not sure, maybe not. Okay, we'll try and get that worked out. But in fact, I maybe even have a machine for this. So let me see if I can get this thing to work. If not, I'll just cut this part of the video out. How about that? All right, so I have a wave generator. I wasn't terribly excited about it before, but we'll see if it works now. So, look at that. Can you see that? Yeah, if I put that up here, we can see that. And look, you got a standing wave. You see those nodes that are in there? You see how they're in there? It's actually changing the frequency as it goes, so it's actually changing the number of waves that it has. And occasionally, like there, perfect. Look at that. Those nodes are not moving, and then all of a sudden it changes speed, and then you change the number of nodes that you have. So you actually get a wave generator like this. Can have multiple, depending on how fast it's vibrating, it can have multiple points along the standing wave. Kind of cool. So there you go. We'll talk more about standing waves in a little bit. Real quick addendum to that. I want to show you guys what a sound wave looks like. So I'm going to hit this thing. It's actually going too fast. I don't even know if you can see it on there. Dang it. You can kind of see the things vibrating. So it's doing this, and that's how the sound waves are moving. They're moving like this through the air.